In this last video about Z and T tests, we're going to talk about when we're wrong, type 1 and type 2 errors, and when we're right. Power of a test is one of the ways in which we're going to be correct. The example we're going to use is a potato chip manufacturer, and they want their chip to contain 2.0 milligrams of salt each. Having made potato chips for a long time, they know that the salt content varies normally with a standard deviation of 0.01. That, of course, would be the population standard deviation. For each batch, a sample of 50 chips is randomly drawn. If the sample is found to be significantly different than 2.0 milligrams at a 5% significance level, then the batch is thrown out. So let's list off what we know. We have our population mean. This is the target that the company wants, and this is the population standard deviation. We have our null hypothesis. Whenever we take a sample of 50 chips, our null hypothesis is going to be that the sample mean is not significantly different than the population mean. The alternative is that it's not the same. Right, which means this is a two-tail alternative, because whether the chip has too much or too little, in both cases we want to throw the batch out. So there are really four possible outcomes to being right or not. Two of them are correct. We can reject the null hypothesis when we should reject it, meaning that the alternate hypothesis is true. That's a correct decision. And if we accept the null hypothesis when it's actually true, that's also a correct decision. All right, which means the two others, of course. The type 1 error is when we reject the null hypothesis, and we shouldn't. And, of course, the last one, as you might guess, is the type 2, which is when we fail to reject the null hypothesis, when we accept the null hypothesis when we shouldn't, when actually it's wrong and the alternate is what's true. That's a type 2 error. Now, I did mention the power is one of the ways that we do correct decisions, and it turns out to be this one. When we reject, when we're supposed to reject. That's the power of this particular test. So we can ask the question, what's the probability of rejecting a null hypothesis when it shouldn't be rejected? The type 1 error. This one is actually the simpler of the two types, because really it's defined by the significance level. The probability of rejecting when we shouldn't reject, 5% in this case, because we're using a 5% significance level. And the reason is that if 100 batches are tested, about 5 will be rejected as not having the correct salt content, when in fact the salt content is fine. It's just those particular 50 chips that is due to random chance happen to have too much or too little salt. The batch as a whole is actually fine. And you can see that. I'll do a quick normal distribution. All right. Here, here is our batch, and we're taking our sample mean. These are actually our sample means. All right, well, there's a chance that just due to random chance, a sample mean might be kind of low or kind of high just because those particular 50 chips had a lot of salt on them. But in fact, the whole batch is the same, but we would end up rejecting the whole batch given that. Now, type 1 is really just this significance level. Fairly straightforward. Type 2 is where things get a little bit more interesting. What's the probability of failing to reject, right, so we're accepting, failing to reject the null hypothesis when it should be rejected, right, meaning the alternate is true, right, type 2 error. Now, this, unfortunately, is a trickier question. In this case, the batch really does have too much or too little salt and should be thrown out. But it's almost the reverse of what I was just talking about. But these particular 50 chips used in the sample happen to not show it due to random chance. These particular 50 chips, the sample or the whole batch has a lot of salt, but these 50 chips, not as much as the rest of the sample, so it comes out looking like it's fine when it really isn't. So in order to calculate this probability, we need to know how much salt the batch actually has, right? In this case, maybe the one that we're going to be doing soon, it has too much salt. But we need to know how much salt it really has, the whole batch, the batch mean. Because it's not what it's supposed to be. We actually don't know. It's something that we can't really determine very easily unless we actually literally measure every single chip in the whole batch. The solution is to go back to the chip company and ask for the range of acceptable salt content and use those boundaries. For example, if the company says that any batch with a mean salt content of 2.05 or more should be thrown out, we can now calculate the probability for a type 2 error. It's going to be specific to when a batch has this mean salt content and using the same 5% significance level, which means this question actually, as it's stated, can't really be answered. It's too general. The only way to answer a type 2 error question is to reword it and be specific. What's the probability of failing to reject the null hypothesis given an alternate mean batch salt content of 2.05 milligrams, which means the batch really should be rejected? Specific, we can only do a type 2 error analysis against a specific alternate hypothesis. All right, so now if we look at our sampling distribution, and this is centered on our 0.2 milligrams. Oops, typo. Of course, it should be centered on 2.0 milligrams. And we need to dimension out the 3 standard deviations on both sides. For that, we need our standard deviation of sample means, which I've calculated over here, which means now we can dimension that out. And we have our sampling distribution. What we can do now is find the lower and upper bounds for our 5% significance level, because that's going to define when we reject and when we fail to reject. Of course, our lower bound, we have 5%, it's 2 tail, so the area is going to be your 0.025, 2.5%, which is going to equal that. There's our 2.5%. And of course, it's symmetric, which means our upper bound, 2.027. All right, we have our alternate hypothesis now. I've lined up the second axis so that everything lines up above. So the 2 and each standard deviation, of course, lines up. Now, for this alternate batch, which we know we're given is 2.05 milligrams. Well, 2.05 milligrams, here's the center, right? 2.05 is right around there. So that's where we would expect the actual distribution to be centered on, right, for this particular batch. And right, here is, of course, our region which we're going to fail to reject. And if we extend that down, right, we can see that there's going to be some sample means that even though we should be rejecting this batch because the salt content is too high, a few samples are going to essentially read low, and we're going to fail to reject. And so that's going to be our type 2 error. which is going to be that area, which of course we can use our normal CDF. All right, we plug in, lower bound and upper bound. Of course, goes from here to here. That's where we're going to fail to reject what really should be rejected. We use, the mean for this alternate distribution, and of course its standard deviation. Turns out to be about 5%. All right, so in answering the question, there's a 5.02% chance of failing to reject the null hypothesis given a mean batch salt content of 2.05 milligrams, a batch which should be rejected. This is a type 2 error. When you're answering these kind of questions, identify the type of error it is. That's going to be important. That's part of really good communication. All right, so now let's think about another question with this 2.05 milligram batch. What's the probability of rejecting the null hypothesis, which is in fact what should happen with this, given the alternate, right? This is the correct decision, and this is what's called the power, as I said earlier. So we're rejecting when we should reject. That's the power of the function. Now, we still have the same distribution, or you still have our 2.05 milligram batch. Right? We are looking at rejecting, right, which is out here and out here. So the area that represents rejecting the null hypothesis is going to be this. Right? And so if we find this area, that's going to be answering this question, and is going to be the power of this test. And there you can see I've used 2.027 as my lower bound, and an arbitrarily large number for my upper bound, 5. And notice that, the power is 95%. It's also, 1 minus the type 2 error. Again, this whole thing is 1, so if you know this, all you have to do is subtract from 1. All right, and you can read the power of the test against the alternative of a batch mean of 2.05. So again, just like the type 2 error, power is only against a particular alternative. Which meaning that the batch with a mean of 2.05 will be correctly rejected 95% of the time. So people like to actually be given the power because it tells them how often a true rejection is going to happen. Right? It's correctly rejected 95% of the time. That's pretty good. All right, now let's go back to talking about type 2 errors. And we're going to change our quantity. So we're going to go back and say, let's just do another example using not 2.05, but something else. Maybe let's pick 1.96. Now, I've picked this for a particular reason, basically because it causes some problems. If we know that what we're looking for is 2, we know that 2.05 is bad. We want to throw that one out. There's a certain underlying assumption that on the other side, if we go a distance of 0.05, it's also going to be too little, which is going to be 1.95 is bad. But this is 1.96. So it seems to me that this particular batch is okay. It has an acceptable amount of salt. It should not be thrown out. Which also means, is this a type 2 error? The answer is no. It's not a type 2 error. Right, we are failing to reject, which is accepting the null hypothesis, when in fact it's true. This is actually a correct decision. So I had to get rid of that type 2 error statement. So now we can come back over here and plot this on our graph. 1.96 centered would be right around here. All right, and we're looking for the probability of failing to reject. Of course, failing to reject is in this middle part. So that's going to be right there. And we can, of course, at this point, calculate the probability of failing to reject using normal CDF, using our lower and upper bounds for this middle section, and it turns out to be 17.7%. So there's a 17.7%, almost 18% chance of failing to reject the null hypothesis given a mean batch salt content of 1.96. Failing to reject is in fact the correct decision in this case. So when we have a batch content of 1.96, we only have about an 18% chance of getting it right, which is kind of too bad. If we continue here, right, if this is the correct decision in this case, another question might be, what's this area represent? Well, this would be rejecting, because it's in the rejection area, when we shouldn't. All right? We shouldn't be rejecting this. It's actually fine, but we are. Right? Well, that's a type 1 error. So if we calculate this area, we're in essence calculating the type 1 error, which would be worded like this as a question. And we can calculate using our normal CDF as we've done in the past. Lower bound, I use an arbitrarily small number up to 1.973. And again, if you know this, all I have to do is subtract that from 1 to get that, perhaps easier. So we have an 82.3% chance of rejecting the null hypothesis, which means we're going to throw the batch out, even though we shouldn't throw the batch out. And this is a type 1 error.